Welcome back. So this is lecture 44 in this course on Bayesian modeling. The topic of today's lecture is regression model examples, right? So we are going to talk about more examples on regression modeling in the Bayesian framework. In the past couple of lectures, we discussed Bayesian regression modeling for Gaussian likelihood, for Poisson likelihood, and for binomial likelihood. In this lecture, we are going to talk about some more practical examples. So, for example, in reaction time or reading time studies where you use a log normal likelihood. Okay, so we'll take a more real life kind of example. So, kind of data that you typically model. Okay. So, let's say um, you want to test a particular effect, right? And we can maybe just take we can continue with examples on word recognition, right? So you are doing a word recognition study, right? And what happens in these word recognition tasks is that uh, participants see some string written on a screen. Okay, so for example bktr, or in the next trial they might see a word like this, and their task is to recognize whether it's a proper word, meaningful word or not, right? So they would recognize it with a key press, right? So they would answer with a yes or no using a key press. Okay, what we are interested in recording here is the recognition time. Okay, so how much time do they take to recognize whether it's a word or not? Now there are several factors. If you think about the underlying cognitive process that produces these recognition times on this word recognition task, there are several factors that can underlie these word recognition times. So for example, we already discussed one of the factor, that was frequency, right? So if you are more familiar with the word because you are using it a lot, or you have seen it a lot in your corpus or in your language uses, you would recognize it more easily and you would recognize it faster, right? Versus a word which is less frequent, right? So the frequency would affect how fast you can recognize it. There could be other things like length of the word could also affect how fast you recognize it. So if for a long word, it would take longer to recognize it, right? One manipulation we already have in this experiment is that whether it's a word or non-word, right? So would it take faster for word compared to a non-word? Yes, so that's a valid hypothesis. So for words that actually exist in your memory, it would take faster, because once you see this, once you visually process it, you retrieve this word from your memory. But for this case, you won't be able to retrieve any word from memory. You might search in your memory for possible candidates, but you don't find it, so you answer with a no. So this process might take more time compared to this one, because in this process you just have to do a lexical retrieval that you can do faster. In this case, you might do multiple retrievals as well, or maybe your retrieval fails, right? So because of that, we expect that words are recognized faster than non-words. Okay. Now, in order to test these hypotheses, the real life experimentation happen like this. What we do typically is that we take a list of words and non-words. Okay. So let's say you take a list of 500 words and 500 non-words, or let's say 250 words and 250 non-words, whatever way you want to do it. 250 words and 250 non-words, and non-words are generated corresponding to each word. Among these 250 words, let's say 125 words are high frequency words and 125 are low frequency words. Okay, to test the effect of frequency. Okay. So the design is like this. So basically, you are manipulating frequency. Okay, so where frequency could be high frequency versus low word frequency. Frequency is manipulated high versus low, and there is word type or string type, which is a proper meaningful word or a non-word. Okay. You of course test the effect of frequency within words. So this is the design. So you can test whether words are recognized faster than non-words and whether high frequency words are recognized faster than low frequency words, right? The number is like this. These are 125, these are 125, and that's what makes the total words 250, and non-words, corresponding non-words are 250 as well. Okay. So this is fine. Now suppose when you do this experiment, you call total, let's say 40 participants. So each participant will read 250 plus 250, 500 strings. Okay. So we will get word recognition times for we will get actually these many observations of word recognition times. So 40 into 500. Okay, so that's a lot. So around 20,000 observations. Okay. So this is the actual experimental data. That's how it may look like. So what we are going to do, we are going to simulate fake data for exactly this experiment, and then we are going to test these hypotheses using regression modeling. Okay. So let us first generate fake data for this particular experiment. What are our assumptions? Let us describe them first, or let me just generate fake data first, then we can think about the model. Okay. So you have words versus non-words. So number of trials is 500. Okay. Then a string type. Now let me write it like this. Number of words is 250. Number of non-words is 250. Okay. Number of trials is number of words. Well, actually that doesn't matter. Now a string type is either a word or a non-word. So let's say it's either a word or a non-word. And how many times do we want to repeat this? So let us repeat this. $250 into, and how many subject do we want? 50, let's say. So into number of subject, 40, let's say. This is variable string type. You can also have subject ID. So subject ID would be repeat 1, 2, and subj. Each should be repeated because each participant will see 500 total items. So each participant should see and words plus and non-words, right? That is subject string type. You can also have frequency factor, so where you will have high frequency or low frequency, and actually it would be okay to, let's say, I just randomly sample from this how many times. Number of words into subject, replace equals to true. Okay, so that is frequency variable. Now let us define mu log as, so let us define some true parameters. Okay, so alpha true equals to let's say 6. Okay, and mu log is I want it on numeric scale so that it's easier to do further calculation. So let's say if it is high frequency word, I will write 1. If it is low frequency, I will write 0, or let's say -1. So interpretation changes. Let us do it with 0. Now this is type if else string type is equals to word, then you have 1, otherwise 0. Okay. Okay. Now mean parameter of a log normal distribution. So don't worry about it. I'm just generating fake data. This is how, let's say this is the true generative process. Let me write the true generative process. This is what I'm trying to simulate. What I'm going to assume is that this is the true generative process, that recognition time for ith word comes from a log normal distribution with parameter mu in for the ith word or whatever non-word, and some sigma, where mu I is equals to some alpha plus beta 1 into string type of the ith word plus beta 2 into frequency of the ith word, right? What does it mean? So let's say frequency is high, then mu I should be low, right? So basically the negative estimate for beta 2, and beta 1, to what extent word type affects this mean, right? So if it is, let's say, non-word, then you should have larger mean recognition times, right? So that's what I'm going to do. Okay, so alpha true I have defined as 6. Okay, so the parameter alpha I have defined as 6. Beta 1 I'm going to define as, let's say, 0.3. I think it's quite large even still. And let's say beta 1 is, let's say this is 0.5 and this is 0.25. Beta 2 is 0.25. And let's say sigma is 0.4. Okay, so these are my parameters. So let me first calculate mu. So mu is alpha plus beta 1 into type beta 2 into frequency. So that will give me mu vector. Oh, not frequency, frequency dot m. That's on numeric scale. So these are the mu values I am getting. Okay. Now I can create recognition time. So let's say empty RT frame is empty RT vector is repeat NA how many times? So they are total n words plus n known words. Okay. Into n subj. Okay. Now for I in 1 2 length RT RTI would be RL norm. So we're going to generate from a log normal distribution, right? RL norm. Let's say one observation at a time. Mu for the ith word, and then sigma, true sigma. Okay. Why I'm doing all this is just to show you that for modeling, it is important that you generate fake data and test your model, whether your model is recovering the parameter values well. So basically, I'm generating some ground truth, right? So I'm generating these data from some generative process that I assume to be true. So you can call it the ground truth, right? So it is always important to check that during model comparison and during parameter estimation, whether you can recover the ground truth, right? And it's a very good practice to have. So you should know how to generate fake data, right? So that you know how the actual underlying generative process might be working. It's also important when you define the model. So when you define the model like this, you should know how this model would generate data. Okay, this is just a model, but you still need to know how this generates data. Okay. So now I think you will have RTs. So this is how RTs look like. Let me just see a histogram to see if everything is okay. Okay, so this is how your recognition times look like. Now I'm going to store them in a single data frame. Dat data frame subj equals to subj, item equals to repeat 1 to 500 each twice, each 40 times, number of subject times. Okay, subject item, then you will have a string type equals to string type, then you would have frequency equals to frequency. Okay, so this is your data. Oh, sorry, RT we forgot. Okay, RT equals to RT. Okay, if you want to see your data frame, this is how it looks like. So this is how a typical data from an experiment looks like, right? So the first column is subject column, then some item or trial ID column, then this is one factor that you are manipulating, a string type, whether word or non-word. This is another column that you are manipulating, low frequency or high frequency, right? So this is how the data looks like. Now let us test our hypothesis of interest. Okay, so let us begin. What is our hypothesis? So H1 is this, that words are recognized faster than non-words. Basically, we can think of it, this hypothesis, in this sense that for words, the average recognition times would be faster than non-words, right? Similarly, what is H2? high frequency words are recognized faster than low frequency word. Okay, so these are our two hypotheses. Now, how do we test them using a linear regression model? So first we need likelihood assumption. So we need to specify these hypotheses in our model and then make predictions from these hypotheses about model parameters. So that is an important step. So first we specify the model that reaction time, recognition time for the ith string comes from log normal distribution with mean parameter mu I and sigma, where mu I is a linear function of word type and frequency. Type of ith string and frequency of ith string. So one thing you might have noticed here, I have actually made mu I as a function of two predictors, not one here. So mu I is a function of word type, string type, as well as frequency, and you can do this. Okay? So what we are doing here, we are introducing multiple predictors in a single regression model, and you can always do this, and that's the main advantage of regression modeling. So this is fine. Now what does it mean to test these two hypotheses within this model? Well, hypothesis 1 predicts that beta 1 should be less than 0. Okay, if you assume that word type is encoded such that that words are encoded as 1 and non-words are encoded as 0. So for words, recognition time would be smaller. So that means the beta 1 should be less than 0. Okay, so for words, recognition time should be smaller. Okay. So H1 predicts beta 1 is less than 0. H2 predicts beta 2 is less than 0. So high frequency words would have smaller recognition times, right? So actually it would be better to have predictors type M and frequency M because these are numeric ones. Okay, so let us just again see how our data looks like. So we have RT column in the end, subject, item, string type, frequency, type M, frequency M. So what type M, frequency M are doing? So type is 1 if a string is word, if it is non-word then type is 0. Similarly, frequency is 0 if it is low frequency and it is 1 if it is high frequency. So basically I'm converting these predictors on a numeric scale, right? So I'm making these predictors numeric so that that's what we need for the model, right? If you don't do this, model will automatically turn them into 1 0 1 0, but you may not know which one is 1, which one is 0. So it is better to beforehand code them as 1 0 1 0. This is called actually contrast coding. We will have a more discussion about this. So there are different types of contrast you can set here depending on your hypothesis. Right now what we have set as contrast is that non-word are 0, word are 1. So this just changes the interpretation of the intercept. Okay, because type M is 0, so that means the intercept is basically the average recognition time for non-words. That's how the intercept should be interpreted. Non-words and low frequency words. Anyway, so now how do we write the model? So in the model, RT is now predicted by type and frequency both. So we include both the predictors in a single formula, right? Data is dat. Now family is not Gaussian. We were assuming log normal likelihood. So log normal. Okay. So here we had log normal likelihood. Now for priors, because you are assuming a log normal likelihood. The interpretation of alpha, beta, and beta 2 will be on log scale, right? So alpha is on log scale, beta is on log scale, beta 2 is on log scale, right? So it couldn't be this as large as this, right? So on log scale, the correct intercept would be somewhere around, let's say 6 or 5, right? So let's say I choose a prior 6, 1.5, that's reasonable enough. For B, for beta, let's say normal 0, 1, that's reasonable enough. For sigma, normal 0, 1, reasonable enough. When you define this class B, which is for the slope parameters, it has defined the same prior for both slope parameters. So beta 1 and beta 2, they are two slope parameters in this model. So it has defined priors for both of these. But the prior is same. If you want to specify different prior, you can do that. You have to write coefficient here, okay, and you have to name the coefficient. Okay. So now our model is all set. So let us fit the model and test our hypothesis whether the data is consistent with these predictions, whether beta 1 is less than 0 and beta 2 is less than 0. Okay, so let's see. So it is compiling. Now this might take some time because the data set this time was quite large, okay, and you have two predictors rather than one predictor in your model. By the way, data would not support these hypotheses because the actual true beta parameters that you use to generate the model were positive, right? So the model is going to give you positive estimate, right? So it is not going to give you negative estimate because the data was generated using positive estimate of beta 1 and beta 2. So it takes some time now because there are a lot of data points. So you have 20,000 observations. So the progress is a little slow. So it's almost 50% sampling is done. It might take another minute or so. We will also see how to back transform to get actual difference between words and non-words, the actual difference in terms of recognition times between words and non-words. Because what this model will give you will estimate of beta 1 and beta 2, which is on log scale, by the way. So I think model fitting is done. Let us plot M1. Yes, chains are mixing well. It has given us estimate of intercept, beta 1, beta 2, and sigma. You can check the summary statistic. These are summary statistics for intercept. So intercept 95% credible interval is between 5.99 and 6.01. So you were able to recover the posterior correctly because the true value of intercept was 6. Similarly for type M, the true value that you've taken was 0.5. So this posterior recovery is good. Similarly for frequency, you took an effect of 0.25. So this recovery is also good, right? Of course, it does not support your hypothesis. It goes against your hypothesis, right? Which is fine in this case because the actual data that we generated assume that these two estimates are positive. Okay. Now let us, so but in this case, what you are getting is an effect size on log scale. Okay, so this is not very interpretable. If someone asks you that how much is the difference between words and non-words in recognition time as estimated by the model, or how much is the difference estimated by the model between high frequency and low frequency words, it's not clear from here. It's 0.25, but it's on log scale. So we want to get it on recognition time scales. So how do we do that? We first extract posterior samples from the model using posterior samples function. Okay, now posterior samples contains the samples from the posterior distribution of all the parameters, right? So let us get so the estimate for alpha. So alpha estimate is like this. So this is a posterior distribution of alpha. Okay, so let me call it alpha post. So what is the posterior distribution of alpha? Post samples intercept, right? What is the posterior distribution of beta 1? Post samples effect of type M, right? Similarly for beta 2, it would be posterior samples for frequency, right? For the effect of frequency. Now we can we can back transform these to get recognition times. How do we back transform? These things are on log scale. So if we do this, so let me get word type effect estimates. So these are still posterior estimates that you're going to get using this, right? So these estimates are exponent of alpha post plus beta 1 post, right? Because for words the value of type M was 1, for non-words it was 0. So this is going to give me recognition times, estimated recognition times only for words. Okay, you can visualize how it looks like. So these are recognition times only for words. And by the way, these are just median recognition times. You cannot get mean recognition times. I mean, there will be different formula to get mean recognition time because this is a log normal likelihood. But this is fine for our purpose. And this is the median recognition time for non-words, because for non-words type M value is 0. So I just have this intercept, right? And this is how it would look like. And this is the difference between words and non-words. So if I subtract this, and this is how the difference looks like. Just let me get 95% credible interval. So this is the 95% credible interval of effect estimate on the recognition time scale. So this is now not on log scale, but the actual scale. So this much is the difference between words and non-words estimated by the model. Okay. This is the 95% credible interval of that effect estimate between 249 and 262. Okay. You can do the same for frequency effect. So this is frequency effect estimates. So alpha post plus beta 2, that's it. So the frequency effect is somewhere between 112 and 122. So these are back transformed effects. So this is the difference of median recognition times in high frequency condition versus low frequency condition. What are median recognition times? Actually, if you see the plot, this was your data. On x-axis, let me have RT and let me group it by let's say a string type. Okay, and also color equals to a string type, and let me draw a density plot. See, so you get these two lines, these two density plots. These are showing distribution of recognition times in words and non-words. So the distribution is not normal, it's log normal distribution. Okay, so you get two medians. So the median for the words is somewhere here, I think around 700 or so. The median for non-words is somewhere here, around I think 500 or so, right? So this much is the difference between words and non-words. So the estimate that we were getting here when we back transformed, we were getting this estimate right here, this estimate. This is the estimate of difference between these two medians of words and non-words. Similarly, you can get one for high frequency and low frequency words as well. So let's say if I write frequency here, now this median difference should be around 100 or so. So this is the difference in high frequency and low frequency ones, right? All right, so here we did a more practical example. This is actually the kind of data that you see in word recognition studies, which with a lot of observations and with multiple subjects. And we tested some theoretically important hypothesis using some fake data, where we had to use two predictors rather than one, because we were testing two hypotheses in a single model. Okay, so that is pretty much doable here. Okay, so our 95% credible interval told us that the predictions are not supported by the data, right? But of course, in order to make the claim that there is no effect of frequency, you will need to do model comparison. That claim you cannot make based on this. Okay, so this is it for this lecture. We used a log normal likelihood example. In the next lecture, we will do a couple more practical examples of linear regression modeling. We will take another kind of behavioral data apart from these word recognition experiments. Okay. All right, I'll stop here and see you in the next lecture. Thank you.